Hello boys and girls, this is Mr. Kizik, and in this video here we're going to be looking at polynomial functions and basically what their general behaviors would be for any polynomial function here. But before we get to that, what is actually a polynomial function? A polynomial function is in the form of like what you see here. I know there's a bunch of letters here, and you might be like, what the heck? But when we throw in some numbers, you'll understand what it means. So basically, you're going to have some sort of term here with an x, maybe, and then it's the descending powers of those exponents. As it says here, 0 is not part of your leading coefficient here, because if anything was 0, then it just goes away. And there are no negative exponents. So we call that term that's in front of a variable, well, what do we call the term in front of a variable? We call it the coefficient, but we call this the leading coefficient. So if I look at some examples here, all right, of the degrees and the function and the leading coefficient. Of this function here, f of x equals 4, the degree is 0 because there is no variable, there is no x. But the leading coefficient is still 4. But I look at the next one, f of x equals negative 5x plus 1. What is the exponent of the variable? Or the highest exponent of the variable? It's 1. And then what's the number, or the leading coefficient of that? Negative 5. Next one, what's the highest exponent in that one? Oh, it's 2, so it's a degree of 2. And what's the leading coefficient of that? It's 12. If I go to the next one, the degree is 3, it's the highest degree. And its leading coefficient is negative 1. Next one, the highest degree of the variable is 4. And the leading coefficient is negative 3. And then the last one here, the highest degree we have here is 5, and its leading coefficient is 9. So based on that here, we can generalize what the parent functions of each of these degrees look like. So what does a constant look like? Well, a constant look like the first one here where there is no degree. F of x equals some value, we'll call it c. And it's just going to look something like this, just a horizontal line going through whatever that number is. What does a linear function look like? Well, you guys have been told or learned y equals mx plus b. But what does the parent function of that look like? Remember, a parent function, when we talked about quadratics, means you don't add, subtract, multiply, or divide anything to that highest degree term. So a parent function of linear just looks like this. F of x equals x, and your line going through that. There is no b term, there is no m term, there's no number in front of x, that's it. So same thing with a quadratic, what we talked about before, f of x equals x squared. It's a squared term that I'm not adding, subtracting, and multiply, dividing anything. And it's a U-shaped graph. Now a cubic function, what do you think the exponent looks like there? You'd be right in saying the exponent cubic would be 3. Now you may or may not know what that parent graph looks like, but it looks something like this here. Now these 4 right here definitely should know generally what they look like. But what about the rest here? What about a quatric function, which is going to be f of... As a loading, yeah, I gotta refresh it. Apologize for that. Yeah. So with a quatric function, you can agree that it's to the 4th power. You may not know what it looks like. It actually looks like the quadratic, but a skinnier looking u. And then quintic, which is to the 5th, actually looks like the cubic function, but again, a little bit skinnier. Let me just look at the 2 there. So what does that mean there? What can we see or what can we discover about the end behaviors of some of these polynomial functions that are adding or subtracting or multiplying and dividing by certain terms here? So if we look at a couple here, 4x to the fourth plus 6x cubed minus x. So if we look here, we have, I totally forget the numbers, right? 4x fourth. Where is that? Wasting time here trying to find it. Trying to find the little caret thing and it's just not clicking in. Huh, where is that? What does that do? Different ones here. Oh, there we go. Knew I had to find it. To the fourth. Oh, to the fourth. And then plus 6x, what was it here? Cubed minus x. All right. So, thank goodness. Okay, so if we look here, what does it look like? Well, and the question is asking what's the end behavior. So yeah, you got this funky little stuff going on right here, but the end behavior as x approaches negative infinity, so as you go further to the left, and approaches infinity, as you go to the right, they're both approaching infinity here. They're both getting higher y values. Well, what if I have negative x squared plus x? So let's do that one. So negative x squared, negative x squared plus x. What does that look like? Again, something going around right here, but if I look here as I approach to the left and to the right, now it's going down. So my end behavior is negative infinity because it keeps getting smaller y values. Well, what about the next two here? So if I look here, the difference between these two, 1 and 2, their degrees were both evens, right? 4 and 2, but one was a positive leading coefficient and the other one was a negative leading coefficient. Well, what happens if I have a odd degree here? So like 2x cubed. So if I graph that here, y equals 2x, y equals, there you go, 2x cubed. It's kind of like what we did when we did the cubic function, the parent. The left side goes down and the right side goes up. So as I get further to the right, it keeps going up, but as I get further to the left, it keeps going down. Well, what happens again if I have an odd exponent, but the leading coefficient is negative? In this case here, what happens if it's this? Well, as you can see here, it just basically flip-flops. The left side goes up, keeps going up, and the right side keeps going down. So as I get further to the right, I keep going down, but as I keep going to the left, it keeps going up. And if I looked at 5 and 6, I have the same concept. So what really happens here? Well, looking at this chart here, these are the things that happen. If I have an even degree with a positive leading coefficient, I'm going to keep going up in both directions. But if I have an odd degree, the left side goes down and the right side goes up. Well, what happens if it's negative? Well, just think of the word negative as the word opposite. The opposite occurs here. For an even degree, both sides go down. For an odd degree, the left side goes up and the right side goes down. So if I look at an example here, if I look at these two pictures, I want you to determine what is the sign of the leading coefficient and whether the sign is of the exponent, or if the exponent is either even or odd. So if I look here, my n behaviors, both sides are going down both sides are going down. If I look at my picture here, my little table, if both sides are going down, then it has a negative leading coefficient with an even degree. It was kind of like the first one we did here, except it was going the opposite direction. Here, I'm going down on the left side and up on the right side. Well, where does that match my table? Down on the left, up on right. Well, that's a positive leading coefficient with an odd degree. Right? With practice, you'll be able to determine what the n behaviors or what the polynomial function would look like based on the n behaviors. I'm going to stop the video right now. This will be part 1, and then part 2, we're going to look at basically how we can get these little things that happen between the n behaviors. Again, if you have any questions, please feel free to